Dear colleagues, today we start our second session of NDTCS 2021 workshop, and I want to introduce our colleagues from Azerbaijan, Professor Metanat Mihrabova, and for today we have only two presentation. Yes, today we have two presentation, and then we are finished. We will finish our conference. Okay, Metanat, Professor Mihrabova, your time.
Thank you very much.
No sound.
No sound. Why?
У них слышно все.
Не слышно?
Okay, start.
Okay. Are you here, me?
Yes, we hear you.
Okay.
Everything is okay.
Okay, thank you. Thank you. I welcome everyone in the conference and wish success in the work of the conference, and thanks the organizing committee of the conference in Minsk. My name is Metanat Mihrabova. I am from Azerbaijan. I work at the Institute of Radiation Problems of Azerbaijan National Academy of Science. The topic of my presentation is ab initio calculations of electronic band structure of cadmium manganese sulfur magnetic semiconductors. I would like briefly inform you about my institute organization. Azerbaijan National Academy of Science was established in 1923 in Baku, and now it joined 43 institutes. Currently more than 10,000 employees, including 4,700 scientific workers, 581 doctors, and 1925 PhD operate in ANAS. There are 67 active and 100 corresponding members in ANAS. In this slide, we can see some views of institutes of Azerbaijan National Academy of Science. This is the Presidium, main building of ANAS, the Institute of Physics, Geology Institutes, Institute of Radiation Problems, and Conference Hall. Now I would like to inform about magnetic semiconductors. This material are very unique properties. They are properties of semiconductor materials and magnetic materials. And there is again for spin splitting in low magnetic field. We can manage the properties, physical properties of this material by a variation of magnetic atoms and magnetic field. And there is again Faraday rotation in low magnetic fields. Magnetic semiconductors are very wide areas of applications, such as optic isolators, gamma radiation detectors, X-ray detectors, solar panel, magnetic field detectors, photo detectors, and etc. In this slide, you can see the Bolotnikov group from Brunhaven Laboratory in New York. His group worked on the problem of creation of radiation detectors on the base of cadmium manganese sulfur magnetic semiconductors. Advantages of A2B6 group-based magnetic semiconductors are following: wide band gap from 1.53 till 2.5 electron volt. High photosensitivity of this material at room temperature, and we can manage the band gap and physical properties of this material by variation of transition metal elements such as manganese, barium, and cobalt, etc. And some information about areas of application. One of the area of application is solar panel. Cadmium telluride and cadmium sulfur-based semi-magnetic semiconductors and the solar panels on the base of this compounds is leading with over 6% of overall solar panel manufacture. Copper, indium, gallium, selenite is emerging with 1% share. Heterogeneated amorphous silicon about 5%, and crystalline silicon dominates with 90% share. The next area of application is the radiation detection. This material have the high sensitivity for registering ionizing rays, operate at room temperature in comparison with another materials, and without of scintillator material. The work purpose of our investigation, ab initio calculation of electron band structure of ideal and defective cadmium mangan sulfur semi-magnetic semiconductors. We consider the defects in this material as vacancy of cadmium and sulfur elements. Work structure, we carried out ab initio calculation in the framework of density functional theory by using atomistic toolkit program of Quantum Weiss firm of Denmark. The calculations are performed within the spin polarized density functional theory and local spin density approximation. We use the Hubbard correction potential for manganese is equal to 3.59 electron volt. On double zeta double polarized basis, spin polarized pi tier 1 basis set with FHI pseudo potential. We calculated band gap density of states, total energy of cadmium mangan sulfur magnetic semiconductors of various supercells. Firstly, we calculated the band structure for cadmium sulfur compound. For satisfy these results, our results was literature date, and then our results was a good agreement with literature date. We calculated the band structure, defined the band gap and total energy. Then we constructed supercell of cadmium mangan sulfur of 8 atoms. One manganese atom replaced the one cadmium atom. In the first line, you can see before optimization the calculation results, forces and stress. After optimization relaxation, forces disappear and stress decrease. You can see the bulk configuration of supercell of 8 atoms. 1 mangan atom, 3 cadmium atom, and 4 sulfur atom. We calculated density of states, defined the total energy. Then we constructed another supercell of cadmium mangan sulfur of 64 atoms. You can see here the bulk configuration, and here this magnetic moments indicated the ferromagnetic phase of this crystal. Forces before and after optimization and stress show the forces disappear after relaxation and stress decrease. Band structure show the Fermi level shifted to conduction band, and band gap is equal to 0.36 electron volt. We define the total energy for supercell of cadmium mangan sulfur of 64 atoms. And we calculated density of states. The partial density of states show that energy levels in conduction band near the Fermi level formed by S atoms of mangan, S states of mangan atoms, P state of mangan atoms, mainly P states of cadmium atoms, and here you can see the these states of S atoms. But energy levels in valence band mainly formed by S atoms of S states of mangan atoms, P states of S atoms, and the deep energy levels in valence band formed by the atoms of S states of cadmium atoms and S states of S sulfur atoms. Then we consider the defective cadmium mangan sulfur supercell of 64 atoms. We choose the bulk configuration with one cadmium vacancy and one sulfur vacancy, calculated the band structure, define the band gap, and calculate the density of state. The results show that Fermi level in cadmium vacancy shifted to valence band. The band gap is decreased and total energy changed too. And results of our calculations, it was defined that increasing of mangan atom concentration leads to increasing of band gap and decreasing of total energy. Cadmium and sulfur vacancy in the crystal structure leads to increasing of band gap, shifting of Fermi level towards the valence or conduction band, and decreasing of total energy. These results you can see in the table. Thank you for your attention. Your question, please. Any question?
Well, thank you for your presentation.
Thank you.
And do you have any experimental investigation using materials which you simulated in your work?
Yes, so we parallel carry out the experiments. We obtained the cadmium mangan sulfur thin films, and we defined the region for obtaining of this crystal of perfect crystalline structure, and then investigate the optical properties of this material, where we can obtain the band gap, and we define the band gap before gamma irradiation and after irradiation. And we compare these results, experimental results, with our theoretical investigation, and the results are a very good agreement.
And do you have any results with with usage of these materials in the real electronic devices?
Yes, these results we will use in our next stage of our investigation for solar panel devices and gamma radiation detection. Our the next aim of plan in this.
And what about your group? Do you use any other software for simulation, or only ATK software?
We use the Atomistic Toolkit program with license. Our group of instabilization problems with my doctorates with my colleagues, about four persons, work on the problems with software, artificial calculations.
Okay, thank you for your interesting presentation, and I hope that we will have possibility to cooperate in the near future with your group, with you, my group, and I wish you all the best. Thank you for your time and for that you find possibility to take part in our workshop. We are very pleased to you. Thank you very much.
Thank you. It's a great pleasure. Thank you.
Wish you all the best. Okay, the next presentation is ab initio simulation of heterogeneous graphene properties. Belarusian State University, Dr. Mishchenko. Please.
Generated graphene properties. The author of this presentation, Valentin Muravyev, and I am Valery Mishchenko. We present Belarusian State Radioelectronics and Informatics. Our presentation consists from the first part, introduction. Graphene has been a subject of many recent investigations, used particular transport, mechanical, other properties, but past investigation show the problem. Some problems connect with the lack of the graphene band gap, which prevents its direct use in digital electronics. As you can see from the figure number 1, figure 1A, you can see features of arrangement of carbon atoms. And figure 1.B, you can see a zone diagram of graphene. Chemical modification of graphene, in past named as graphene, and recently entered for investigation as a possible candidate to solve this problem. Graphene is a compound which consists from the two-dimensional graphene, which covalently bonded by some atoms of the hydrogen. Graphene is a semiconductor which have novel structure, low dimensions, and it's possible to create similar structure using by other atoms such as the fluorine, lithium, and some other. We propose that research of modified graphene structure is important for the fundamental science and technology application. For example, most interesting direction in the high-speed transistor structures operating in the microwave and very high frequencies range. To this purpose, in our work, main task is to investigate parameters and characteristics of hydrogen graphene by ab initio method. Part number 2, my presentation, methods, some words about method and peculiarities of simulation of hydrogen graphene properties. We complete ab initio calculation, have well-known quantum espresso code, quantum espresso program complex, using well-known PB parameterization of gradient approximation named GGA, well-known. In our calculation, we use some energy parameters, restricted energy parameters, 40 Rydberg energy wave function cutoff, 1030-50 reach change density cutoff. Brilliant zone has been sampled using grid 24 Banvai Manhos-Pak grid. Yes. Next part, our results of our modeling. We complete some stage. First stage, we relaxed structure. Relaxed structure use 100 persons and 50% hydrogen fluorinated graphene. In literature, this structure named as H sub 100 persons, H by 50 persons, F 100 persons, and so on, respectively. Our results, as we compare our results with results of the authors, is quite agreement with results got at these authors. Some of our results, not all, we presented by figure 2 and figure 3. On figure 3, you can see figure 2. You can see figure 2 sub A shows peculiarities of arrangement carbon atoms, carbon and hydrogen atoms. Figure 2.B presented calculated zone diagram in the structure 50% hydrogen-generated graphene. We used in our text notation C sub 2, C H1 type. As you can see, for the structure, main features of the structure placed atoms of the hydrogen placed above the plate of the atoms, the carbons. Analysis of the zone diagram show us that we have open distance between conductance zone and valence zone. We assume that our results may be in good agreement with simulation data obtained by more precise GV method, but we don't complete calculation but with this method, but communicated information delivered from the other researchers concerned accuracy between in range 5%. All materials that we consider are semiconductor which have not degenerate conduction band minimum G point, some exception concerning some structure with fluorine atoms. Then we have instructed some parameters. Among these parameters, effective mass of electrons from result of our structure using density functional theory DFT GGA simulation. Next figure number 3 presented results of our simulation arrangement carbons hydrogen atoms. On the left you can see this structure atoms of hydrogen placed above and under plate of the atoms carbons atoms. In the right position you can see simulated zone diagram. The structure make it 100% hydrogen structure. Each atoms of carbon accordance we have 1 atoms of hydrogen. Additionally, from our simulation we get some results concerning calculated total electrostatic potential. I show results sometimes earlier, sometimes later. From the analysis of the figure 2 and 3, we make next conclusion. This materials is characterized of the three-value GM carbon diagram. Value G is characterized as the smallest energy band of between conduct and valence bands. Next, material concerning calculation total electrostatic potential distribution. I'll show the two figures. Figure number 4 give us results of our calculation total electrostatic potential V sub Bear plus VH Hartney plus V exchange correlation components for the structure 50% hydrogenated graphene. You can see this figure in green. We can see in the center of this figure. You can see two atoms of the carbon. Low from the one atom, you can see one atom hydrogen. You can see line connected with the special table is the left upper corner of this diagram. In the figure 5, we presented essential diagram similar electrostatic potential distribution, but don't include component potential Vxg. But comparison of these pictures 4 and 5, that allows us to estimate exchange correlation potential, and then use this data in other programs. Next stage to use this information is the program Monte Carlo program. As I say, we use this data to get effective electron mass of graphene. Some modification. For example, I don't include information about this all value of this material, but effective electron mass of graphene of 50% value for the G value is equal 0.787. Yes. In conclusion, next stage, part number 4, conclusion. Repeat some information. We complete ab initio simulation of hydrogenated graphene properties. Calculation have been performed by use of quantum expresso program complex code for the structure 50%, 1000 hydrogenated graphene structure. We extracted effective mass and other parameters from the results of density theoretic DFT GGA simulation. The use of graphene with such characteristics, it possible, as we assume, to achieve to construct in future graphene transistor structure with open band gap, use these materials in digital electronics. High mobility and high speed of charge carriers make graphene and its modification is a promising material for the creating new semiconductor devices with a good output characteristic. In the end, you can see reference of some literature used in our presentation. That's all.
Thank you very much.
Thank you.
Thank you very much. Any questions?
How do you estimate a distance between carbon and hydrogen atoms?
Difference?
Distance.
Distance. This distance we calculate use by relaxation this structure. In quantum expressor, special first stage. I don't say about the stage relaxation. About this relaxation, I have digits placed between the carbons and hydrogen atoms. This information don't include in private communication. I will give, if you want, I give you this information.
And do you know any experimental results about possibility of construction of such structure?
Experimental results.
Such types of structure.
Other authors get it. We know these results, but I don't know results of using this material in a transistor structure.
But the results of with obtaining or with realization of such types of structures.
Yes, these results
presented. Yes.
Yes, in literature, this describes this result.
Okay.
Structure get this result, but I don't know results where this material used in transistor structure. It's our purpose to get information how introduce, it may be introduced, but some characteristics maybe will be definitively obtained. Don't get in our stage, we don't get some characteristic of this material. We'll propose this to get this in future, next stage.
Okay, thank you very much. Thank you very much for your participation, for your presentation. And finally, dear colleagues, thank to everyone who was able to take part in our conference. In particular, I would like to thank Professor Merker, who is the father of our conference, to Rector of Belarusian State University of Informatics and Radioelectronics, Professor Bogush, to Rector of MIREA University, Russian Technological University, Professor Kuch, to President of MIREA University, Alexander Sigov, our partners, LG Electronics Company and Joystock Company Integral, and to his administration. The use of high-tech approaches in science is an urgent trend in modern world. Proof of this can be considered the fact that over the long history of workshop, it is only developing and attracting more interest. From the small event in circle of well-known colleagues for more than 20 years of history, the workshop has turned into large event. The 19th International Workshop different from the previous one. Firstly, it was integrated working format. Most of the speakers spoke online. Secondly, for the first time, we held a remote session together with MIREA University. This should definitely strengthen partnership between our universities. I can say with confidence that the workshop was successful, and with a light heart, but with sadness to declare it is closed. Hope to see you all at next event. I don't know where, but maybe in Minsk too. I wish you health and professional success. Organizing committee will send all of you information about publication processing. Any question you can send to our official email. Thank you and goodbye. I think see you again. See you soon. Thank you very much.